Right. Good evening, engineers. Welcome to another edition of Event Learning. I hope you guys had a wonderful holiday season, and we're glad to see you on this training, our first for 2021. So for tonight, we will be discussing the overview of piping design. Okay. This training is provided to you by Even Learning. Even Learning provides quality trainings and seminars conducted by your peers. In this training, you would learn how to size chilled water piping, calculate the pipe pressure loss, and some useful apps and programs that we use. This training is approximately about 1 hour, including the question and answer portion. As we go along the training, if you have any questions, please feel free to write it on the comment section if you're on Facebook or on the comment section on Zoom. We will get to them during our Q&A, or if you have some questions that are unanswered, we will get back to you after the training, or you can send me an email at evenlearning.sg@gmail.com. So for tonight, I will be speaking with you. I will be your instructor. My name is Donnie Gabriel. I have more than 20 years of experience in designing and installation of air conditioning and mechanical ventilation systems of various applications. I am an alumni of Mapua, and we will start. Let me share to you guys my screen. I see that we have quite a few participants for tonight. Give me a minute. All right. So you guys can see my screen. So for tonight, we are part 4 of our ACMV series, overview of piping design. So the first part was heat load calculation. Then we have ventilation calculation. Then we have ducting design, and now we're on piping design. Next week, our training will be on ACMV controls. So for tonight, we are doing the overview of piping design. Again, my name is Tony Matthew Calpo Gabriel. I'm a professional mechanical engineer. You can reach me at evenlearning.sg@gmail.com, or you can reach me through my handphone number. My handphone number is listed there. Okay. For tonight, we have 3 topics. First is how to size chilled water pipe. So for air conditioning and mechanical, for air conditioning, no, we will be discussing chilled water piping. So we are not discussing, or we will not be touching any type of piping system, but we will be focusing our attention on chilled water piping system. Then we will see how to calculate for the pipe pressure loss and some useful apps and programs. All right. So first, chilled water piping system. Let's say this is your example of a small office or a room or a small space. You want to air condition this space. So what you're gonna do is you're gonna put your air handling unit. So this air handling unit will provide you, sorry, this air handling unit will provide you cold air and will cool up the room. This room, the room inside the air will be sucked up and returned to the air handling unit. So this is your typical air conditioning system. This air conditioning system, this air handling unit will be connected to a chiller. So once this the heat from this room is extracted by the AHU, this AHU, the heat from the AHU will be then transferred to the chiller. And then from the chiller, it will be transferred to your cooling tower. So this in its entirety is called your air conditioning system. Okay. This, only this, is your chilled water system. So this chilled water system is divided into 2 more parts. First, the chiller and the air handling units, or your terminal units. This is called the chilled water piping system. Okay. The other side, the cooling tower and your chiller, is called the condensing or condenser water piping system. So you have 2 systems, no? You have 2 types of piping, the chilled water piping and the condenser water piping. Both are connected to your chiller. The chilled water piping is the chiller to your terminal units or air handling units, and the condenser water condensing water pipe is the connection from your chiller to your cooling tower. All right. Let's go back to our previous example. Our previous example is your small office. Let's assume that your small office has a total heat load of 500 kilowatts. So when the AHU is blowing air to your room, the room is being cooled down by the cold air, and the hot air is being sucked back to the air handling unit. So this 500 kilowatt is actually being transferred to the air handling unit. So assuming this is the 500 kilowatt of incoming heat load from the room, inside the air handling unit, you have a heat exchanger. This heat exchanger transfers the 500 kilowatt of heat load from the room to the air and then to the piping system. We'll just ask for the participants to please mute yourselves. Thank you very much. All right. Okay, going back. So the 500 kilowatt of heat load from the room will be transferred to the water by this heat exchanger inside the air handling unit. So theoretically, this piping, this connection from your chiller to your air handling unit has water carrying 500 kilowatt worth of heat load. So the heat load from the room will be transferred to the air handling unit, and this air handling unit will transfer the 500 kilowatt to your chiller through by the means of your chilled water piping. So our problem now, or our discussion now, is how to size this piping system. How will you know how big this piping will be? Okay, so let's calculate. Since we are assuming that the total load from your room will be transferred to the air, this total load we assume also will be transferred to the water. So we're not going to consider heat transfer loss. No, we're going to consider that the full total heat load will be transferred perfectly throughout each systems. So the heat load from air will be equal to the heat load from the water. So this is our formula. Q is equal to mCp delta T, where Q is the water cooling capacity, M is the water flow rate, Cp is the specific heat of water, and the delta T is the difference of temperature in the water, the difference between supply and return water temperature. So this is the supply, and this is the return. So the cold water will come in, will make contact with the warm air, and this cold water will increase in temperature. So we're looking for this difference in water temperature. Please note that the water temperature is usually, for this system, for the chilled water system, the delta T is usually 5 degrees. Doesn't matter if your 5 degrees is 7 to 12 or 13 to 18 or 6.5 to 11.5 or 7.5 to 12.5, doesn't matter. But please check your chiller manufacturer. Based on your set points, the chiller manufacturer will provide you the most efficient chiller. So go and check with your chiller manufacturer what are the set points or what are the delta T that the chiller they provide. But usually it's at 5 degrees. Okay? So assuming at 5 degrees, assuming that our chiller is at 5 degrees. So Q is equal to mCp delta T. So 500 kilowatt, our assumed room heat load, times the properties of the water, we will get about 1,428 liters per minute. So this is at LPM, liters per minute. So this 500 kilowatt worth of a heat load would need about 1,400 liters per minute of chilled water. So now we already have the water flow rate. Based on this water flow rate, we can determine the appropriate size for this water flow rate. So to determine the appropriate size, we use slide rule or we use software or an app. Okay, this is the two software that this is the software that I usually use. This is what I personally use to size up my piping. This is the digital one, and this is my slide rule. Okay, below I post the link where you can get these things. But personally, I use these two things. Okay, so unlike ducting, piping system or piping has a standard sizing. So we don't need, there's no such thing as 1 1/8 diameter pipe. No, there is, you can ask them to manufacture for you. But commercially, you have your standard pipe sizes. So I already put down here the standard pipe sizes, okay, there in red color. This is the standard pipe sizes. Based on the standard pipe sizes, our industry standards for designing piping will be based on two factors. Either it's based on velocity or based on friction loss. Friction loss is the pressure drop or friction drop per meter of your pipe length. The velocity is the speed of fluid going through your pipe. So for the velocity, the industry standard should be 2.2 meters per second or less. The fluid inside your pipe should be traveling at maximum 2.2 meters per second. This is what they deem to be safe. So at 2.2 meters per second, this is the maximum fluid velocity inside your pipe, or 300 pascal per meter of pressure drop. This 300 pascal per meter of pressure drop, this is the balance between the pressure drop and the pipe size. So you won't see any books telling you 300 pascal per meter or use 2.2 meters per second. These two parameters is the industry standard. This is the usual standard or the usual practice being used within the industry. So when you're sizing your chilled water piping, the design parameters are usually based on friction or velocity. If it's for friction, 300 pascal per meter, provided that the velocity is less than 2.2 meters per second. If the velocity is 2.2 meters per second, that would be your maximum, regardless of your pressure drop. The pressure drop should be less than 300 pascal per meter. So when we calculate this pipe size and this pressure loss or velocity, we will get the standard flow rate. All right. So this standard flow rate now is based on your standard pipe size. So going back to our problem earlier, we need 500 kilowatt worth of cooling capacity or heat load. We can easily select this one, higher than 450 but less than 735. So we will be choosing this pipe size. At 500 kilowatt, 1,428 liter per minute, the pipe size should be 150 or 6-inch. Again, take note that the pipe size mentioned here, or the pipe size that we will mention, whenever we say pipe size, we will always be referring to nominal pipe size. What is nominal pipe size? Okay. Nominal pipe size refers to pipe non-specific terms and identifies the diameter of the hole with non-dimensional number. Okay. So this is your inner diameter of the pipe. This is your outer diameter of the pipe. This is your pipe nominal diameter. It's not necessarily the center or in between the outer diameter and the inner diameter. It's just the nominal diameter. Nominal diameter are usually indicated with DN, dimensional number, or NPS. So this is the indication or the symbol for or abbreviation for nominal pipe size. Okay, so going back, for our 500 kilowatt worth of cooling capacity, we would need 1,428 LPM. We would use 150 millimeter diameter of pipe size. Okay, so our supply piping and return piping would be of same size, 150 millimeters. How about on the other side? How about on the chilled water side? The condensing water side. The condensing water side, same process, same parameters. However, your cooling tower, usually the delta T is 5.5. Please check with your local manufacturer what is their equipment specifications. You can change this 5.5 to whatever delta T that you would want, provided that the manufacturer will be able to achieve or able to comply. Sometimes they would some designers or some consultants, I would see that they would specify 5 degree delta T. Some would say 6, some would say 4, some would say 5.5. It's up to the designer and up to the capability of the cooling tower manufacturer. The higher the delta T, The bigger the fan, the lower the delta T, the smaller the unit. So same parameter, same process, Q is equal to MCP delta T. You would see because the delta T is high, the flow rate is lower. Now our flow rate for this 500 kilowatt is only 1,299 liters per minute. So again, same pipe size, same standard pipe size, same parameter, friction and velocity. Friction should be at 300 Pascal per minute, per meter, sorry, 300 Pascal per meter, not exceeding 2.2 meters per second in velocity. So based on our table, we would need to use 125 millimeter of pipe or 5-inch piping. I put here both SI and IP units. Some of my colleagues, they could not visualize SI units but could easily see IP units. For me, it's the opposite. When I go to the site and then my contractor will tell me that's a 4-inch pipe. In my head, I will be converting 100 mm. So I put here both the IP units and the SI units for convenience. So again, on this side, on the condensing water side, the 500 kilowatt of cooling capacity or heat load, it will be will require 125 mm of condensing water piping. System configuration for the chilled water system. Sometimes you would have a few terminal units or a few AHUs. Few AHUs, let's say all of these are duty, all of these are running. So 500 kilowatt to Office 1, Office 2, Office 3, Office 4, all on duty. Usually, on the chiller side, you have spare units, spare capacity. It doesn't have to be 1,000, it could be 500, whatever the consultant would want or whatever the client would require. But usually, they would have spare units. These spare units is when other chillers or other units are in maintenance or preventive maintenance mode, the standby unit can pick up the slack. Before I continue, is there any questions so far? No? No questions yet? All right, I'll continue. All right. So, how do you connect this terminal units or this AHU to your chiller your chiller side? Okay. So, this is the simplified version. First, you have your distribution pipe. Your distribution pipe, then you have your main pipe, and then you have headers. All right. So, this is where it gets interesting, these headers. Let's say you have 500 kilowatt each. So 500, 500, 500, 500. Total 2,000. Based on our previous table, this 2,000 kilowatt would require 250 mm diameter piping. So this is 250 mm. 250 mm, 250 mm, 250 mm. Here, you would notice that this 2,000 kilowatt, the pipe increased. Your pipe headers are usually one size higher than the required size. Why? By putting one size higher, you are removing the fact or you are removing the pipe loss associated with the distribution. So example, this distribution pipe, 2,000 kilowatt, this water doesn't know if it's going to this, or this chiller. Because anyone can be duty, anyone can be standby. Let's say it's this one. If this piping is connected to here and this piping is connected to here without the pipe header, these two will have a different pressure drop or will have a different pressure setting. To avoid that, to nullify or to have the pressure drop from this point to this point, negligible, regardless of which chiller you're going to, you would put pipe headers. So example, the pressure drop from this chiller going to this, going to the to this one will be same pressure drop if you're using this chiller going to here, going to here, going to the last terminal unit. Okay. So for your distribution side, if you have parallel connection, to nullify or to disregard the pressure loss going to each of your units, you put header. Headers are usually one size higher than your required pipe size. It's the same principle on the cooling tower side. Here, let's say duty standby. Usually, chillers and cooling towers are 1-to-1. They're always a pair. One cooling tower to one chiller. They always come in pair. So if you have 2 units of chiller duty and 1 standby, you also have 2 units of cooling tower duty and 1 standby. Nevertheless, it is regardless to which chiller or which cooling tower you are using. You can have this as duty standby, or you can have this as duty standby duty. It doesn't matter. Why? Because you have pipe headers. That's the purpose of your pipe headers. On the cooling tower side, aside from your distribution pipe headers, and your main pipe, you have one more pipe, equalizing pipe. This equalizing pipe is piping connection between cooling towers to ensure that the water flow or the water level for all cooling towers are equal. So if this pump is running, it doesn't matter which cooling tower he would be getting, because all cooling towers will have the same water level. Usually, the equalizing pipe is one size lower than the required pipe size. So for example, our previous example earlier, we need a 2,000 kilowatt or 2 megawatt of cooling capacity. The pipe size required based on flow rate will be 250. Your header will be one size higher, 300. And your equalizing pipe will be one size lower at 200. All right. Any questions so far? So that's how you size your equalizing pipe, your pipe header, and your distribution pipe. Your main pipe are only the combination of your distribution pipes, so it's easy to calculate. And we have the table to use according to standard pipe size. If your pipe size is bigger than what is on the table, you can easily calculate, as long as your velocity is maximum at 2.2 meters per second. That's how you size your chilled water piping. So now we calculate for the pipe pressure loss. So here on the condensing water side, the water from the cooling tower flows to the chiller, then from the chiller sucked by the pump, then go up and discharge to the cooling tower. This side, the cooling tower side, is an open loop piping system. Because it's an open loop piping system, your pipe pressure loss, or let's say the pipe pressure loss is always equal to the friction loss, but we will use the pipe pressure loss as to the static pressure required by the pump or the pump head. Your pump head, if it's an open loop system, will be the difference in height from the lowest point to the highest point. So this is the height that's required to be overcome by the pump. The pump head will be equal to the difference in height. So this one, the difference between the low point and the high point, plus the frictional loss. The water will flow through the pipe and its fittings and will have its pressure loss. and the required pressure. This required pressure is the pressure loss on your equipment, on your cooling tower and on your chiller. Because once the water travels to your to your chiller, this chiller itself has a pressure loss as required by the manufacturer. When this pump this pump discharges water to the cooling tower has a required pressure discharge. So this required pressure is specified by the manufacturer. So pump head for the condensing water side is the difference in height, friction loss, and the pressure requirements as specified by the manufacturer. So here is the chiller manufacturer and the cooling tower manufacturer. So let's say the difference in height is 5 meters. So from the base of the cooling tower to the top portion of the discharge is 5 meters. The frictional loss at 300 meters per pipe length, 300 Pascal per meter, assuming at 300 meter pipe length, we can calculate. 5 foot is as per requirement of the manufacturer. On the pipe slide, on the slide rule, okay, I will go back. Let's go back here. Our example earlier is a 2,000 kilowatt per 2,000 kilowatt of 2,000 kilowatt of heat load. At 2,000 kilowatt, earlier we have calculated there 1,299 liters per minute. 1,299 liters per minute times 4, 1.3 times 4, about 6, 1.3 times 4. There. 2.6 liters per minute. At 2.6 liters per minute, we use the, we could see here at 200, this is 200 mm piping that we have sized earlier. The actual flow rate is 2,600. From this slide rule, we are able to determine that the actual pressure drop is 100 Pascal per meter. 120 Pascal per meter of pressure drop at 300 mm pipe. However, this 300 mm is not straight pipe. It has bends, it has T's, it has elbows. So what is the pressure loss on those fittings or pipe fittings? These are the nominal pipe size and common pipe fittings. So example, 200 200 mm pipe size. So this is 200 mm pipe size. On your 200 mm pipe size, you have one elbow. One elbow means 4.8 meters. An equivalent of 190-degree elbow is an equivalent of 4.8 meters of pressure drop. So 4.8 times 120. That will be the equivalent pressure drop for your elbow, 90 degrees, at this pipe size. So on your shop drawing, no, on your piping layout, you can quantify how many pipe fittings you have, how many elbows you have, how many T's you have, how many valves you have. And using this chart, you'll be able to get the pressure drop on each pipe fitting. Each pipe fitting plus the pressure drop on your straight pipes, then you will get your pressure loss throughout your pipe. So for example, our previous example, you have 5 meter of height difference times our 120 Pascal per meter of pressure drop on straight pipes. For our example today, we will only assume the pipe fittings will be at 50% of the pressure drop by the straight pipes. And then 5 feet as per manufacturer's requirement. So total of 11.5 bar. For pipes, since it's high pressure, we would use the units of bar. 1.1 is our safety factor. So 5.9 bar for the height difference, 5.4 bar for the pressure loss across the pipe, and 0.15 bar for, as required by total of 10.45 times 1.1 as safety factor. You have 11.5 bar as your required pressure static pressure head for your pump. So the 11.5 bar is the pipe pressure loss from your cooling tower going to your chiller, going to your pump, back to your cooling tower. So this is the open loop piping system. How about on the other side? On the other side, from the air handling unit to your chiller, you would see that this is a closed loop piping system. Since this is a closed loop piping system, there is no difference in height. There's no pressure need to overcome by the difference in height. So you only have the frictional loss and the required pressure for the equipment. We go to the previous example earlier. Let's say that this one is equivalent of 300-meter pipe. Again, at 1,000 kilowatt, because you have 500, let's say 1,000 kilowatt, you have, 2,000 kilowatt, you have 200 mm pipe. At 200 mm pipe, you need 2,856 liters per minute. There, 200 millimeters of pipe, 2,856 liters per minute. You have an actual pressure drop of 270 Pascal per meter. Using the same assumption as previous, difference in height, you don't have. Frictional loss, 300 meters length of pipe length, 270 Pascal per meter. Actual pressure drop according to your pipe size and to your flow rate, 1.5 for your fittings. Then you will have, this one is for your equipment. This 5 foot is for the chiller. This 1.21 is for the air handling unit. Note that you're only using one. You're only assuming that this one is on the worst case scenario, so on the longest run or on the farthest pipe. So you're only considering that this pump is able to pump the water from chiller to the farthest AHU and back to the chiller. If this pump can supply for the farthest AHU, it sure can supply to a near AHU. So that's why on our calculation, we only do one, the farthest one. So total 12.42 bar. So this pump need 12.42 bar to suck the water from the chiller, go to the farthest AHU, and back to the chiller. So this is an example of the pipe static pressure calculations sheet. Okay, I will show you the Excel version. Give me a minute. Screen share. Okay. Oh, sorry. Take this one out. All right. So this is an example of the pipe static pressure calculation sheet. So you calculate from the pump all the way to your chiller, then to your air handling unit, all the way back to your pump. So you quantify for each straight pipe, for each pipe fitting, and its equivalent pipe length. A minute. All right. So as you quantify each pipe fitting, as you quantify each pipe size, you'll be able to calculate its flow rate, its actual pipe pressure drop, and the total pressure drop. You add them all together plus your safety factor, then you will have your equivalent pump head. Okay. Question? Question so far? Wala pang question? All right, I'll continue. So that's how you calculate for the pipe pressure loss. Some useful apps and programs, again, like what I've shown earlier. What I personally use is the McQuay, or now it's Daikin. McQuay was bought by Daikin, so I use the McQuay pipe sizer. It's still available for free at daikinapply.com. So anything else? Thank you very much. Any of you have questions?
Hello, sir. Good evening.
Yes, Sir Eric.
Yes, sir. Good evening, sir.
Good
Sir,
evening.
I just want to clarify yung bar per meter.
Per meter.
Yes, sir. Yung sa pressure.
Yes, sir.
Saan ba yun na, sir? Kinuha na yung the value.
Balik ako sa slide, ano?
Yes, sir.
Saan mo nakita yan, sir? Sang part?
Yung sa pressure drop.
Pressure drop. Doon sa Excel ba yon o doon sa ano?
Yung sa sa presentation.
Sa presentation. Sandali lang, ha? Ito ba yun, sir?
Yes, sir. Yes, sir. Yung sa pag-calculate na.
Pag-calculate na. So, ulit natin, no? Isa-isa. Okay, ayan. So, on the chilled waters, condensing water side tayo. So, this is the condenser water side. So, sa pagkuha ng pump head, you need 3 parameters. First is your difference in height. Second, yung frictional loss. And third, yung pressure requirement ng equipment. Okay? So, yung 5 meter height, since ang fluid natin ay water, we could easily convert 5 meters of water pressure into bar. So, nako-convert yun. So, I will stop this screen share. I will share to you my web browser. Where's my web browser? All right. Oh, ayan, nakita nyo, nag-NBA ako. Okay. So, this is the conversion, no? So, you could see here in pressure. There. So, from meter of head to bar. Ayan. So, convert. So, nako-convert yung meter of head. So, 5, since our assumed height is 5 meters, so we could easily convert 5 meter of head into bar. So, ito yung conversion factor ng bar to meter. O, baliktrin natin. 1 bar is equal to 10 meter head. So, nasagot ko ba yung question mo, Sir Eric?
Yes, sir. Yes, sir. Kuha ka na. Simple lang yun sa
simple lang yun. Simple lang.
Thank you, sir. Thank you, sir.
Walang anuman. Anything else? Any other question?
Sir, good evening.
Yeah, good evening, Sir Ken.
Sir, dun sa factor of safety nyo, yung nauna kanina, 10%. Yung pangalawa, 20% na.
Oo.
Saan kayo kumuha ng ano nyo, sir? Saan kayo kumuha ng data na yun?
Okay. Yung first, yung 10%, yun yung usual na ginagamit natin, no? The usual safety factor actually as recommended by the books is actually 5%. For us in our company, we are advised to use safety factor of 10%. However, yung isa, yung 20% na nakita mo, actual calculation yon as required by the client. The client requested 20%. So iba-iba, no? Because the higher the safety factor that you put, the bigger the equipment that you're going to have. So we don't want an equipment that are too big or the factor of safety is too wide. So we only usually, your college books will only say 5% is usually sufficient kung tama yung pagka-calculate mo. Pero kasi sa real world, in the actual practice, you seldom go to calculate in detail. Usually you would go with rules of thumbs and approximation and assumptions. And to compensate for those assumptions, you have to have a higher safety factor. So in our practice, we have a safety factor requirement of 10. But our client, the client requested do sa mga calculation sheets, they requested to have a safety factor of 20. That's why on the assumptions on my slide, it's 10 because that's the standard that we are following. At yung Excel sheet, the actual calculation that was performed for the client requested 20%. Ayun. Nasagot ko ba, Sir Kent, yung tanong ninyo?
Okay lang po, salamat po.
Clear, ha?
Okay na, clear na po.
Maraming salamat. Those were great questions. If you have more questions, we still have a little bit more of time.
Sir, another question, sir.
Yes, sir.
Because our sample is HU. So same approach lang din ba siya for example, chilled water for FCU for the lower capacity?
Yes, same.
So the velocity is 2.2, I think, then this lang 300 Pascal per meter.
Yes, same. Same for terminal units that includes HUs, package cooling waters, fan coil units. Ayun. Pare-parehas lang sila. This is assuming we are sizing chilled water piping, assuming that your system is running at chilled water. So parehas lang yung approach, parehas lang yung sizing procedure. Whether it be HU or FCU, PCU, MAU, pare-parehas lang sila. Thank you, sir.
Thank you, Sir Don.
Anything else? Let me check a little bit. Tignan natin kung merong request or may questions sa Facebook. Wala naman. So kung walang request sa Facebook, walang question sa Zoom, I think it's up to meron daw. Sandali lang. Let me check sandali lang sa Facebook. There. Can you attach the Excel sheet, please? Yes. For those who have registered, for those who have sent their email address, I will send to you the slides. I will send to you the slides that we have used. The video will be uploaded on Facebook, so you can watch it on video. And the Excel sheet, I will also send it to you, so you can have a template how to calculate your pump pressure loss. So I will show you again. Wait, let's screen share. So for this Excel sheet, I also included the equivalent pipe run or the equivalent pipe length. So for your globe valve, for your angle valve, for your check valve, what is the equivalent pipe length? So length in diameter, this is length. Yeah, this is the equivalent pipe length. All right. So the Excel has its references, and also the slides has its references. So you will get both. For those who have opted to get the certificates, the certificates will be sent out separately. But for those who have registered, the slides and the Excel sheet will be sent to you. All right. Thank you guys. So kung wala nang, there's no more comments, there's no more questions, I think we should end early. Thank you very much. We will see you next week. So next week is the ACMV controls. So we will tie up all together, no? The first four, the calculations for mechanical ventilation, the calculations for heat load, pipe design, duct design. We will tie them all together, how the whole system is being controlled. So we will discuss that next week here on Even Learning. Same time, Saturday, same channel, Zoom, 7:30 p.m. Next week, January 16. So thank you guys. See you again next week. Bye-bye.